In this video, we will talk about buckling of columns. What are columns? These are long and slender members. And if these members are subjected to axial compressive loads, and in this case, a lateral deflection of columns can occur, and this kind of failure will cause buckling. So the maximum axial load a column can support without buckling is called the critical load. An ideal column is at the beginning, before the force is applied, it is perfectly straight. And buckling will occur, and there are, as you see in this figure, there are two possibilities for buckling. A buckling around X, which is shown in the figure, and also a buckling around Y may be possible. But the buckling of a column occurs around the axis with the smallest moment of inertia. We know that the moment of inertia is the resistance of a section against bending. So in our case, the axis XX will have a smaller IXX, and buckling will occur as shown in the figure. What about the critical load? We have a formula to calculate the critical force, and it depends on the column geometry and the elastic property of the material. E is the elastic modulus of the material. I is the least moment of inertia, and L is the length of the column. The geometrical properties of a column can also be given by a slenderness ratio. Here we have an R, and R is the moment of inertia of the section and the area. Okay, the R value is called the radius of inertia, and it's a measure how a section is distributed around the centroid. If the section consists of areas which are far away from the centroid, then the R value will be large and the section will be more resistant to buckling. So the formula can also be written in terms of slenderness ratio as given over here. Well, in this example, we have a steel column, which is pin connected at both ends. It is asked to determine the largest axial load it can support before it either begins to buckle or the steel yields. So the question wants us to examine, due to this compressive force, whether yielding will begin first or buckling occurs before yielding. For the steel, the yield strength and the elastic modulus are given. Besides, for the section, we have the area and the moment of inertia values for Ix and Iy. We see that Iy is the smaller one, so buckling around Y is easier. Let us calculate the buckling about Y. This is my formula. Elastic modulus, moment of inertia, the length of the column. So we have a critical load 1577 kilonewton. That is the force where buckling will occur. The question is, when I apply this load, what is the compressive stress? Well, if I take this force divided by the area, I find that the stress at this moment is 300, about 300, but the material's yield strength is only 200. That means before I reach this critical force, the material will begin yielding. So let us calculate the stress where yielding will occur, actually the force where yielding occur before buckling. Well, this force divided by the area should be 200, which is the yield strength of the material. So we find out that at 1000 kilonewtons, yielding will begin, and this is the critical failure force. Columns may have various types of supports, and the supports at the end of the column are important for buckling. Well, as you see, we have considered only pin supports where the column at the supports can rotate, but for example, if you take the lower support fixed, so this column cannot make a rotation around this end, so in this case, the buckling will be in a smaller segment of the column. So there is a definition of the effective long LE, which has been made for different columns, and LE is defined as K times actual length, and K is the effective length factor, and it is used to calculate the effect of the supports at both ends. You see in the examples, well, here the K is 1, here K is 0.7, here K is 0.5. If you have a free end, then the K is 2. So let's take an example, a steel column. In the bottom it is fixed, and at its top, so we have a prevention of movement along the x-x axis. So this is my x-x axis. So this end cannot make any movement along this axis, but you see it can make rotation. You can take it as fixed. Well, if you have the y axis, in the y axis, well, the column end is actually free. It can make any movement. So we have two different types of support at the top end. Okay, what are given? Materials elastic modulus, yield strength, cross-sectional area, Ix and Iy values, and we have to calculate the allowable load P for a safety factor of 3. Well, let's start with the y-axis buckling. So the buckling around this axis. So as you see, you can consider this end as pinned, the other end is fixed. So we have a K factor of 0.7. So the actual length is 5 times 0.7. This is the effective length for y-axis buckling. For the XX buckling, you see we can move along the y-axis. So for the XX buckling, well, the supports look like this. We will have a free support at the top end. So my K value is 2 and the effective length will be 10 meters. Let's calculate the critical loads for each case. So when you put the values and the appropriate I values, you find that P critical for the X buckling is 1180. For Y buckling, it is 3200 kilonewton. So, which one is lower? This one is lower. That should be the critical load. Let's calculate the stress under this load. 1180 divided by the area gives you 236 megapascal, and the material's yield strength is only 400. So in this case, well, buckling will occur before yielding. So no yielding before buckling. If we consider the factor of safety, it has been said that we have to use a factor of safety of 3. So this load is the critical load. This force divided by 3 is 393. That is my allowed safe load. You see again in this example that a safe load and a critical load are not the same. The critical load is where the failure will occur, and in the safe load you consider a factor of safety, and this load will be much smaller than the critical load. Okay, that was our video about buckling. Thank you for listening.